All right, this is a quick demonstration of computer performance in Labview. I'm actually running a virtual installation of XP on Labview 2010 on a MacBook Pro, but so we'll see how we do here. The thing that I want to do is I want to make a program that just counts to a really, really big number and see how long that takes. I'm going to do that for a few different ways of making that happen. So let's just do one here. And so the thing I want to do is I'm going to drop down a flat sequence structure, and I will put frames at the front and the back, and I will take the value of the millisecond timer on the front end and the back end, and I will subtract those two. And I can create an indicator. Again, I'm right clicking here, time, and that's in milliseconds. So if I go in here and run this guy, well, sure enough, that runs in time 0. So we'll need to do something in here that takes some time. So so one way I could count to really big numbers is using shift registers. Obviously, I could just like tally up the number of indexes, but I want to actually exercise the memory here as well. So what I'm going to do is I'm going to create a shift register, and I will simply increment the shift register by 1, and then let's initialize this, and I'm going to do it with integer math. So notice that when I change the initialization, the +1 can take integers and floats and all different types of numbers. So, and then I will create a control here, which is for loops. So presumably if I type a number in here that's like, I don't know, 100,000, didn't see it, 10 million, so 10 million loops takes 14 milliseconds. So that's good. We're doing a lot of counting here. And one thing that's important to keep in mind is that I can, if I were to put an indicator inside the loop, writing to the screen is expensive, so we'd actually have to watch that thing count, and sure enough, it takes over 10 times longer, and then I should be able to right-click and hide that indicator, and well, actually, we're still doing some updates. So that's probably a little bit, this is probably more representative of where we want to be, because sure enough, we're probably going to have to do some memory management inside the loop. So it goes to show that already we're seeing a factor of, I mean, that's actually more like 20 or 30. So already we've learned something here that that if I force the screen updates, we're running in about a half a second, and if I go in and hide this guy, then we'll seem like we're running a little bit faster than that, about 400 milliseconds now. So that's good. So this is one method of updating our timing here, or updating, doing lots of counting. So I'm going to create a program that measures different ways of doing this. And so the way that I can do that then is I'm going to go in here and I'm going to create an enum. And my enum will be called method. And if I right click and do edit items, I can fill in some things. So here we have a for loop with shift registers. And we can do a, next we'll do a for loop with locals. I can come in here and I can create a case structure and wire case structure up to my enum, and then sure enough the value in here looks like I've misspelled for with fought, so I'll go change that. Fixing my typos, for loop with locals. This isn't the locals case, so I need to right click and say make this current case for loop with shift register. Oh, sorry, that was show. Make this case for loop with shift register. So there's for loop with shift register. So now I need to come in here and for loop with locals. So again, grab a for loop, hire a number of loops, and this time I'm going to need I'll name him for shift, and I'll copy him out to be another one called for local. Come in here, there's my increment. And might as well initialize him as long as. Now technically there's nothing that's going to say that, oops, sorry, not doing a very good job of copying. Got to hold control down when I do that. So nothing to say that this loop over here won't run before or after this guy, but the reality is this is one execution, and this is 110 million executions, I believe. Yeah, 10 million. So, so we might not get this to happen first off. So if I wanted to be a purist here, I actually would need to put in another sequence structure, run the initialization first. But I'm not concerned with the final number. And again, for local is displayed, but so we can run this. And it looks like we're taking about the same amount of time with our locals, which is a good thing. We've got some pretty good optimized code here, and then I can go a little faster. And again, we're running at just about the same speed. Just showing this guy. And so for both the for loops with the locals and the for loops with the shift register, we're about the same time. We can see the for loop update. Let's see, actually we need to get, so there's for shift. So for loop with shift registers, there he goes. And when he's running again, we're getting about 430 milliseconds. And on the for loop, there we're getting just about the same speed. So we're not paying much or any of an execution hit by using locals or shift registers. Now I can go in and I can try this again, but we could do it with while loops. And so, for example, I'll go in and I create one more. Again, I can edit items, and let's see how while loops compare. And we can just compare the case for while loop with locals. Okay. And I don't, on my shift register, notice I still only have two options here. So I can go, let's see, I want to see, make sure I'm at the end, do add case after, and sure enough, while loop with locals shows up, which is great. Already filled that in for me. So I can, this time, create a while loop. I'm going to go back here and just grab a display. So now we have, oops. This is going to be while local. Get rid of that 2 on the end. And we can initialize him again. There's nothing to say that initialization will run exactly the first time. So so I really should put a sequence structure to make sure that this happens before the loop. In fact, just for this case, let's just go ahead and do that. So I will drop in a flat sequence structure, and then add frame before. Starting to slide off the screen here. And there's my initialization case. Here's incrementing. And then what I want to do is I got to figure out when to stop. And when I want to stop with a while loop is, again, when we've counted above the number. Because we're incrementing here, we're actually going to track along with I, so I can do either one of these guys. And so what I'm looking for is that when the number that we're counting is greater than, then we want to stop. And so this is, again, we're on the stop if true condition. Again, I right-clicked on my end terminal here, stop if true. And so now we can try and see, here's my while local, and we can run the while loop. And the while loop, a little bit slower, actually, I guess, than that first one. We're running one extra time, but not too much. And so the thing that happens here is the reason that while is actually a little bit slower, and we're seeing that sort of 50, there's 100 milliseconds slower, is that we actually have to go and do this logical operation. We have to go and calculate what are these values larger, and this logical operation takes a little bit of time, and so that's the reason that the program is running a little bit slower here. So anyway, now we have a way to test the speed of 3 different structures by counting 0 up to 10 million, and in this case, even when displaying those values to the screen, we're doing that all on the order of about a half a second. So there's a quick tutorial on measuring computation speed with Labview.